Thank you very much to everyone here at Connected Data London for inviting us. It's exciting to be here in London, in one of the great cities of the world. I've come here from the US. We are a US-based company, but we have just hired a European sales director. So we are going to be building a local team for not just the UK, but all of Europe and into the Middle East. So my topic today is scaling up business value with real-time operational graph analytics. So really, I'll be telling you how TigerGraph distinguishes itself among all the different graph database products out there. So I'll explain the title as we go on. So our first opening keynote address was from someone from Google. We all know probably Amazon, Google, Facebook. Many of you know Alibaba. They're a China-based company. Just like eBay is an auctioning network that was founded in the US, but it's now worldwide. Alibaba is, I think it's a little different. It's connecting consumers directly with vendors and manufacturers, but it's huge. They've expanded around the world. So these are really showing the scale of these companies. These are driving a lot of the financial markets, and everything they do is either naturally, like Facebook and Google, naturally related to connected data and graph, or behind the scenes, if you only think a little bit about it, is doing a lot with connected data and graph. And so Gartner, a large, well-respected financial analyst and technology analyst in the US, has pointed out they believe graph analytics is the single biggest differentiator that's going to say whether an enterprise is really succeeding or not, is whether and how they employ graph analytics. So graph analytics, the leaders are already using it, and everybody else is seeing how they can. So for those of you that are here to take on that mission, how can you use graph analytics? We're here to try to help you. So if you're going to try to connect not just data, but big data with graph analytics, here are some of the benefits for that. You're going to have richer knowledge from the idea of big data. It should not just be all of the same, but it should represent a wider distribution, a better sample of the greater world. And by using a connected data, the term knowledge graph is often used, and saying some graphs are knowledge graphs. I'm here to say really all graphs are knowledge graphs. It's connecting one fact to another. So that is adding the additional dimensions. You no longer have flat data. You now have multi-dimensional data. As many different types of connections as you have, that is how many dimensions you have. And so that adds to the richer knowledge and information and wisdom. On that, you can then perform better analytics and then ultimately get better results. But there are challenges. You have to store all that data. And now that we're talking about graph, how are you going to store your graph data, this multidimensional information? How are you going to do it efficiently? And if you're going to do more complex analytics, do you have an engine that's properly designed to handle this more complex analytics? The typical types of operations you might be doing. One of the dangers we have is exponential slowdown. As you are doing tasks that are exponentially more difficult, is your product similarly slowing down? And finally, in the end, is it cost effective? Because we're trying to get value. So to summarize, how do you fulfill the promise of graph analytics? It's a wonderful idea, and if you do it right, it will really reap benefits. So I'm going to start by talking about one of our use cases, China Mobile. So China Mobile is, mobile telephone network in China. So therefore, one of the biggest, if not the biggest, telecom in the world. And they had a problem. Just like everywhere, there's a lot of phone scam. People call up, they are trying to engage you in some fraudulent activity. That's the worst case. Less severe is they're just an annoying salesperson. So this is some of the scale of their use. 460 million users. That includes one of the two parties in the phone call is in their network. 10 billion phone calls a month, 10,000 per second at peak need. So they came to us, and we worked with them to develop a real-time fraud or phone scam detection system. And this is an example of what we mean by real-time operational graph analytics. So it's happening real-time as every phone call is being made. And it's operational. This is their fundamental activity. They execute phone calls. So the graph is the network of one person calling another. And remember, that's the size of the graph. And so it's constantly changing. It's constantly growing. They're dropping off the older data. And they're performing analytics on this. So we construct the real-time operational call graph. They take a sample of that to use as training data where historical set of phone calls where they know some of them were fine, some of them they classify as the so-called bad phone calls that they want to try to identify. And then we worked with them to develop 118 graph features. And I'll show you examples of those graph features on the next slide. And they use those features to enhance their machine learning model. So they then ran machine learning on this and then able to then develop a detection model for the type of phone calls they want to filter out. They actually came up with 3 different categories of so-called bad calls. The really fraudulent ones that are just sort of annoying salespersons, and I forget what the third one was. But there are 3 categories of bad phone calls. And then, and natural deployment, as every phone call is being initiated, they run the analytics, which means using every phone call and the past history of who that party has called, they extract these features, and this is real time. So they're traversing the graph in real time to find these features, and from that determining whether this call should be flagged as one of those 3 bad cases. And what they will actually do is, as that call is being made, before you decide whether to answer the phone call or not, if it's a so-called bad call, a text alert shows up on your phone of which of these 3 bad cases it is, and then you can then decide to not answer the call. So it's that fast. And this is what I mean by the graph features. So this here is the person who is initiating the phone call, and based on their current and past activity, we have all the persons they have called and persons who have called them. Here we have these 2-way arrows in this group. So when we say stable group, these are people that over time they've had multiple calls. And so you can think of this as a community of people who regularly call one another. And so that would be a friendship group. These would be considered good calls. Here is where we then look, who do you call? And among those people that you call, do they call one another? So this is saying you are part of a community. This is saying the people that you call, are they a community? And that's another way of expressing a potentially good group. I'll point out that this distinction about which is good and which is bad, in some cases it's not so easy to know. The job of the graph analytics is to simply extract the feature, and the machine learning will decide whether it's good or bad. And this is one more case where you call someone, they call another, and then it comes back to you. And this is actually a chain through friendship. And so these are examples of 3 different features, and we actually had 118 such features. So again, that's an example of what I mean by real-time operational graph analytics. In order to execute this, let me go back. A little learning to use this remote. You need scalability. We're dealing with big data. We need to be able to handle large data. As we talk with customers and potential users, first we were using the word gigabyte, then they come to us with terabyte, now they're talking to us about petabytes. So there's vast amounts of data out there. People are desperate to find a graph platform that can support that sort of scale. So first of all, being a distributed database where you can have your data stored on multiple machine nodes, that becomes essential. To partition your data, to have your data cannot be confined to a single machine as it is in some graph database products. It has to be distributed across multiple machines. And then speed at scale. Everybody does well on small sets of data. Can you do well on large sets of data? And also, to be operational, you have to be able to not just read, but write. So you need good write speed. And obviously, you're going to have to develop queries for this. This is more analytical type work. It's not graph visualization. We're not talking about visualizing these billions of nodes. We're talking about doing multi-hop deep link analytics. And so you need a query language that is good at describing such operations and which, when it's compiled or interpreted, executes in parallel. Because to achieve this speed and scalability, you need some parallelism. We at TigerGraph, we see the graph market as having developed in 3 generations. The first generation was single server. The good thing about it is it was fundamentally, from the ground up, designed as a new product, as a graph database. It's not something that's tacked on to another database or data storage system. But it didn't have the scalability yet. So that was done in the pre-NoSQL days. When NoSQL came around, people then decided we can use this storage platform as a vehicle for developing large distributed scalable graphs, because NoSQL is scalable. But NoSQL, as you know, has limitations. And again, basically it's good for certain types of reads, accesses, where you're reading data in certain patterns or large sets of data. It's not necessarily good for the operational type work that we're talking about, or the real-time read and write. And it's not good for the multi-hop because, again, it's not a native graph. And so if what you're trying to do is hop from one node to another, a native graph database, something that is built, its storage engine is built for that, you can do that efficiently, just like the first generation did. But the ones that are based in NoSQL really don't perform so well on the multi-hops. So TigerGraph represents probably the first of the 3rd generation databases that have native graph storage, that load data in parallel, that perform the queries in parallel, and because of the native design can do the multi-hop actions very quickly, designed for both read and write efficiently, and again, designed to scale. It's a distributed database. So one of the advantages of this design is then you can now achieve HTAP, which is the merging of sort of old school OLAP with OTLP, both transactional. We used to classify databases as either a transactional database or an analytical one. And over the years, we've started to see some platforms that claim to, and some platforms that legitimately can say they have merged these 2 capabilities. But whether these 2 capabilities are available in graph is another question. So I'd say all graph databases are multidimensional by nature. And most of them, at least on smaller data, they have good real-time reading. A subset of those have ACID properties for transactional work and offer good concurrency. And we believe TigerGraph is unique in its ability to, what happened there? TigerGraph is unique in its ability to really offer a full range of doing real-time read and write, doing these compute-intensive multi-dimensional analytics, to do real-time aggregation, and that results in what we think is true HTAP for graph databases. And I'm getting I think I'll just skip over this briefly, or do this very briefly. But this is just showing how when you're trying to implement this model, you're bringing data in from multiple sources. Your operational data, which is changing in time, your master data, somewhat more stable and source of truth, historical data, and as we were describing earlier, if you're running machine learning, you're extracting new features to better tag and add attributes to the data you started with, and then from that you can derive many, many use cases. So I'll try to spend the rest of my time talking about use cases and talking about our new graph analytics, graph algorithm library. This is a sample of some of our customers who are all in some way, even though they have a variety of different use cases. I'm not doing so well with this remote. A variety of different use cases. They're all in some way using graph to not only describe the operations, but also do customer 360, which is, again, describing all the things you know about your customers. What other connections do they have? Okay. And so in doing so, that's really this merging of multiple sets of data and then performing complex analytics on that is the power of the real-time operational graph analytics. So one case I'll talk about is Zillow. Zillow is a US-based leader in e-real estate. They're really transforming how the real estate industry has worked for decades in the US. The idea of going to an agent and having that agent do things for you is being changed, where you can now do a lot of things for yourself on the web. And I'm not going to have time to go into the detail, but you can just quickly see some of the possible things that you can do with graph analytics and their idea of putting what used to be a lot of human transaction and agents having exclusive access to the data. The data is now becoming much more public, and they're bringing tools to help regular consumers and real estate sellers leverage that to their benefit. This is another application, network and IT infrastructure. This is actually a large US bank that we've been working with for well over a year. And so it's not in their financial sector, but, oh, no, sorry, this one is a utility. So obviously, an electric distribution utility is a natural graph. But what to understand there is my undergraduate degree is in electrical engineering. There's a lot of complex systems, mathematics in balancing the electric distribution, doing it safely, efficiently, making sure things don't blow up. They're actually doing all that complex mathematics in the graph. This is the IT analysis I was talking about. This is our way that we have formulated a model for using graph for anti-money laundering. And this is related to the example I talked earlier about with the, with China Mobile, where you're taking your data and you are extracting new graph features, and that is enhancing your machine learning model. And so by using graph-enhanced machine learning, you're better able to do a better job of anti-money laundering. I'm going to have to skip over this because I want to get to the graph algorithm library. Graph algorithm, this is now related to my PhD work. when I switched from electrical engineering to computer science. Graph algorithms are not created by graph database vendors. They're created by people who understand mathematics. So they're out there. They're not proprietary. But what you need is a platform that can implement graph analytics efficiently. And just very quickly, I'm going to have to skip over all this and tell you about a use case. So this is a healthcare network. We use PageRank, not for web analytics, but to decide who is the most influential doctor. Once we find out who is the most influential doctor, we do community detection to see who does he influence. And then by understanding who you influence, the goal is to improve medical care and to improve the cost and efficiency by saying who is influential, who do you want to target for making sure they are using the healthcare system, giving the best treatment, and should they, if they do things a certain way, then by having them do things a certain way, they will influence others and impact the whole healthcare market. So TigerGraph now has a nice graph algorithm library, and the key to our graph algorithm library is it's open source. Our engine is designed for this type of analytics. These are not embedded functions. These are just written in GSQL, our query language. You can look at them. You can modify them. They run very well. I personally wrote some of them. And so I want to just thank you for your attention. I'm sorry didn't really get to everything I wanted to say, but I want to open up the floor to questions. Yes.
How many nodes for the China telecoms?
Again, they have 460 million nodes in their graph. So each node is...
Sorry, how many actual machines do they need to...
They use 5 machines. Yeah, so it's not huge. They have 32 CPU cores and 512 gigabytes of RAM on each machine. Yeah. Another question?
That's running in like AWS or Azure?
We are available. We have machine images on both of those, on AWS and Microsoft Azure. We just introduced Docker images and VM images for our developer edition. So we have a free download of a developer edition, and you can, so previously you had to install it on a Linux machine. Now using Docker or VM, you can install it on a Mac or Windows PC. Yes?
So I understand you have to be really quick as you are using real-time data. So you have to hold the whole data set within memory, as far as I understand.
It is not necessary to put it all in memory. Certainly, some databases these days are branded, I shouldn't say branded, they technologically are in-memory databases. Performance benefits, we do all the data that you are working with, what we call the topology, needs to be in memory when you're actually working with it. If you look at a graph, if you think about the graph structure, just the structure, and this is the way, by the way, when you're running a graph algorithm, people tend to think about just the structure and forget about the attributes. So the attributes can be sitting on disk because they're used less frequently. But to do the hops, you have to know the topology. So the topology sits in memory when you're using it.
The nodes and the edges themselves, that you can quickly traverse multiple hops.
Yes.
Is in memory.
Yes.
The attributes not.
That is, so it's a continuum. We look at how much memory is available, and we load as much as we can into memory. So that's why ours is not a rigid in-memory database. You could have a small amount of memory. It would run slower. We'd do a lot of swapping. But if you have a large amount of memory, then we'll run faster.
Thank you very much.
Thank you.